Hello, OChem2 students. Today I'm going to be showing you how to do NMR and interpret NMR from two different examples using ethanol and aspirin. We're going to talk about four things: the number of signals that ethanol and aspirin have, the position of the signals, the integration of the signals, and the spin-spin coupling. So first off, as we look at the structure of ethanol, we can see that there's a total of 6 hydrogens, and there's only going to be 3 signals. There will be 3 signals because there are only 3 locations where the hydrogens are the same, such as on this carbon, all 3 of these hydrogens have the same basic structure and same environment. Now on this carbon, there are 2 hydrogens that share the same environment. And on this oxygen, there's only this lone hydrogen here. Therefore, we'll have a total of 3 signals. Now, the position of these signals will vary depending on where they are and what they are bonded to. Because this signal is bonded to an oxygen, it'll fall between the 2 to 5 range on the NMR. These 2 hydrogens are both bonded to a carbon that is next to an oxygen, so they will also be shifted downfield by about 2 to 3 ppm. These last 3 hydrogens are pretty normal and will fall within like the 1 to 1.2 range. Now for integration, this hydrogen bonded to the oxygen will only have an integration pattern of 1 because there's only 1 hydrogen, while these 2 hydrogens will have an integration of 2 because of the fact that there's only 2, and these last 3 will have an integration pattern of 3. Now the spin-spin coupling comes based off of the N+1 rule, which takes the number of hydrogens on the neighboring carbon and adds 1 to it, and that'll show how many peaks we will have at that location in the NMR. So for the 3 hydrogens, they're next to a carbon with 2 hydrogens and nothing else. So therefore, using the N+1 rule, it'll have a triplet peak, which is 3 peaks right next to each other. While the 2 hydrogens are next to 3 hydrogens, so they will have a quartet. And this hydrogen that is bonded to the oxygen has no neighboring hydrogens, so therefore it'll show up as a singlet. Now that we know these 4 things, we can interpret an NMR structure and learn how to find the same things from the other direction. Because we know there will be 3 total signals. The OH will be from 2 to 5, the CH2 will be from 3 to 5, and the CH3 will be from 1 to 1.5. Next, we'll then look at the integrations, and we can see that the OH only has 1 hydrogen because it's next to, or it has only 1 hydrogen on the oxygen. The CH2 has 2 hydrogens because there's only 2 hydrogens, and the CH3 has 3. We'll know that OH is a singlet, CH2 will be a quartet, and CH3 is a triplet because of their neighboring hydrogens. So as we can see from the NMR of ethanol, we can see 1 signal, 2 signals, and 3 signals in total. Now, the position of these signals are: 1 is at around 3.7, 1 is at around 3.6, and 1 is around 1 ppm. Now, we can also see that this farthest signal is a singlet because there's only 1 peak. The second farthest signal is a quartet because there are 4 peaks. And the last signal is, or the furthest upfield signal is a triplet. Now, just looking at this, we already can tell which ones are which based on the spin-spin coupling, and I have blacked out the integration just to make it a little bit more challenging. But we can then determine that since this hydrogen is going to be the furthest downfield and have a singlet, we can determine that this singlet right here is the OH. Next, we can look at the two hydrogens on this carbon, and we can determine that it'll be the second farthest downfield because of its position. And also we can determine that it has a quartet as well. So it'll be these peaks right here at 3.6. The last three hydrogens will be the least far downfield, and we'll have a triplet. It'll be the least far downfield, and it'll show as a triplet. So therefore, we can determine that this triplet is that one. Now I'm going to clear all this out. Now that we have determined that this farthest peak will be the OH hydrogen, the second peak will be the CH2 hydrogens, and that this peak will be the CH3 hydrogens. I'm going to remove the, to see the integration, which we can already guess as the CH3 being 3, the CH2 being 2, and the OH being 1. And as we can see, we have correctly guessed which peaks represented which hydrogens. Next, we're going to talk about a more complicated molecule that is very common in medicine and in pretty much overall life, aspirin. So as we can see, first we're going to look at the number of signals. As we can see, this oxygen contains a hydrogen, and there are no other hydrogens like this environment. So this will register as a single signal. There's no hydrogens on this carbon, no hydrogens on either of these two carbons. But then these two may seem like they should have the same environment, but actually, since this is one away from the carboxylic group and two away from the ester, or ether, sorry, and this carbon or hydrogens are one away from the ether and two away from the carboxylic acid, these two will actually have differing environments. Now, these two hydrogens on the ring will also have different signals because of the location. The same reason as the other two. They're either two away from the ether and three away from the carboxylic acid, or vice versa. However, sometimes on an NMR, these two will read as one because of overlapping. Now, the last signal is this CH3 right here, which will have its own signal because there's no other environment like it. So we'll have a total of 1, 2, 3, 4, 5, 6 signals that may look like 5. Now, the OH signal will be the furthest downfield because it is part of a carboxylic acid, so it'll be around 10 to 12 ppm. Now, this hydrogen signal will be the second furthest downfield because it is directly next to the carboxylic acid group, and therefore it'll shift. It'll already shift based on being in the ring, but then it'll shift just an additional further than the rest of the rings because it's next to the carboxylic acid. The next further shift will be this hydrogen right here because it is next to the ether group, and therefore, and it is also in the ring, so it'll have a shift around 8 as well, but a little bit further. Now, these two will have similar shifts because they're part of the ring, and they're either 2 or 3 away from the ether and ester, depending on which direction you go and which one you pick. And they will almost register the same. The signals on the NMR may overlap, so they might only appear as one for that reason. Now, the least downfield shift will be from this CH3 molecule because it's part of an ester, but it also is only a CH3, so it's not part of a ring or part of a carboxylic. And it'll probably be around anywhere from 2 to 3 ppm. I'm going to label the ring hydrogens as A, B, C, and D so that they're easier to mark and be read. The one closest to the carboxylic will be A. This one will be B. This will be C. And this will be D. Now, when talking about the integration of the signals, we just have to determine how many hydrogens are on that carbon or oxygen. So this OH group will only have an integration of 1, and so will all 4 of the aromatic hydrogens. And the CH3 group, since it has 3 hydrogens, will have an integration pattern of 3. For spin-spin coupling, we've still used the N+1 rule. And so for this OH, there are no neighboring hydrogens, so therefore N is 0, so +1, we'll see a singlet for this. Again, at around 10 to 12 ppm. Hydrogen A is next to 1 hydrogen, and therefore it should register as a doublet. However, there should be some interactions between, since it's on a ring, that may cause it to have a bit more signals being read. So since it's a doublet initially, it may have a doublet of doublets. However, we're still just going to follow the same N+1 rule. B is next to 2 hydrogens, 1 from A and 1 from C, and therefore it'll read as a triplet. C will also read as a triplet because it's next to 1 hydrogen from B and 1 hydrogen from D. And D will also just read as a singlet. Will also just read as a doublet since it is next to only 1 hydrogen at C. Again, all 4 of these may have some coupling interactions that cause it to have different looking peaks, and also sometimes in NMR, our peaks are not very precise if the instrument is not correctly set up or used. And so therefore it may not always appear that they are doublets or triplets. However, we can determine based on the shift, if not, and the integration, if we're given the integration. Now the CH3 right here has a singlet as well because it has no neighboring hydrogens, just like the carboxylic OH. Okay, so now that we know all 4 of these qualifying factors to the NMR, we can now look at the NMR and determine which signal is which. Now, looking at the NMR, the first thing that stands out is that this little singlet peak right here at around 11. And looking at our position of all the signals, that can only be our OH group. And since the OH has an integration of 1, we'll know that this will have an integration of 1 hydrogen. And since it is a singlet, we definitely know that this is our carboxylic group right there. We also, the second thing that stands out is this large peak at around 2.2. We can tell that this is the CH3 peak because CH3 has a shift from 2 to 3, and the integration is 3 hydrogens. So we'll know that this is equal to 3 hydrogens. Now, and we also see that it is a singlet. Now, as we can see here, around 8, there are 3 signals, which are zoomed in on right here. Now, like I said before, hydrogens B and C have a similar environment, but they're not the same, so there will be some overlap. And so if we look at this farthest downfield signal, we can see that it registers as a quartet. And because it registers as a quartet, we can assume that there was some coupling interaction since we have no quartets. And it most likely is our doublet from carbon A, since it's the furthest downfield, since it is next to a carboxylic. So this will be A, and it'll have an integration pattern of 1 hydrogen. All right, now the second farthest downfield has 4 signals as well. And this only shows us that it can be the same reasoning as A having 4 signals and B also a doublet. But the only doublet left is D, which should be the second farthest downfield of the ring hydrogens. So therefore this signal is D, and it'll also have an integration pattern of 1 hydrogen. Now, this last signal has about six peaks, and therefore it's probably the interaction between B and C, since they are both triplets. So this registers as both B and C, which also should be the least far down field, because they are the furthest away from the carboxylic acid and the ether. But this will right here will have an integration pattern of 2 hydrogens solely because of the fact that it's counting for both signal B and C. However, if we had them separated, B would only be 1 hydrogen, and C would only be 1 hydrogen. Again, added, there are 2. I just want to be clear, I accidentally keep referring to this functional group right here as an ether. It is in fact an ester, and this is still a carboxylic acid. I hope that helped you identify on an NMR which peaks represent what, and how to determine the position, the integration, the spin-spin coupling, and the total number of signals. Thank you for your time, and thanks for watching.